Alright, so this is 9.6, solving exponential equations. This is our practice page. Example 1 asks us to solve 3 to the x equals 15 to 4 decimal places. The one thing I want to tell you about each one of these problems, I love that they're each different. Some of them are things we've just done. Some of them are going to draw on things we've done in the past. But all of these are the types of problems you would need to know how to solve. Alright, so for this first one, it's just a straight up equation. Whenever we're solving for an exponent, I need to remember that my method or my tool for solving for an exponent is to take the log or natural log of each side. Because there's no e involved in this problem, I would just take the log of each side. So the log of 3 to the x equals the log of 15. And I know from my properties of logarithms that that exponent can be moved to the front. And I get x times the log of 3 equals the log of 15. I want to solve for x, so I'm going to divide both sides by the log of 3. And I'm just going to put that into my calculator. Log of 15 divided by log of 3. And it says to 4 decimal places. That 7 is going to bump the 9, which is going to bump the 4. So I get 2.4650. Right. Example 2. A family has $15,000 in a savings account that is paying interest at a rate of, that is a 0.8%. So I know as a decimal that would be 0.008. If the interest is compounded continuously, as soon as I say that, I know that I'm going to be using my PERT formula. How long would it take to grow to $35,000? Well, my principal amount is $15,000. My rate is 0.008. I don't know the time. That's what I'm looking for. And I want to have $35,000. So now I'm going to solve. I know that because of the e, I'm eventually going to be taking the natural log of each side, but not yet. I need to get that e alone. So I'm going to divide both sides by 15,000. 35,000 divided by 15,000. Like a repeating decimal. I want to keep it exact for right now, so I'm going to call that 7/3. So 7/3 equals e to the 0.008t. Now that I have the e alone, I can take the natural log of each side. When I do that, this is simply going to be 0.008t, because remember the base is e. E to what power is e to the 0.008t? Well, it's simply 0.008t equals the natural log of 7/3. Now I'm going to divide, because I'm still trying to solve for t, by the 0.008. And now I'm going to move to my calculator. I have the natural log of 7/3, and I'm going to divide that by 0.008. And I get 105.9. That's a long time, but it's a very low interest rate. It's less than 1%. Okay, let's look at example 3. Potassium 40 decays to argon 40. Just want to make a note. The 40 is just part of the name. It's not going to be a number we use in the equation. It's just its name. Like if you're, you know how, what is that TV show, Stranger Things? Her name is 11. It doesn't mean she's 11 years old or, just that's her name, 11. Well, there is a story behind why she's called 11, but you know what I mean. That's just her name. Potassium 40 is just the name of the substance. Decays to argon 40 with a half-life of 1.5 billion years. That would be 1,500,000,000 years, making this decay suitable for dating the oldest rocks on Earth. If 35% of the potassium 40 found in a rock has decayed to argon, so if 35% of it has decayed, that means 65% is remaining. About how old is the rock? All right, well, when we learned half-lives, we always said you take the principal amount times 0.5 to the total time divided by time and a half-life. And that gives you the amount that you have remaining. Not the amount that's gone, but the amount that's remaining, which is why I wrote over here, if 35% has decayed, 65% is still remaining. So we started off with one rock. I guess we can put a 1 there. It decayed at a half-life. Our total time, we don't know. That's what we're looking for, but we know what our time and a half-life is. 1,500,000,000. And we know that we have 65% remaining, or 0.65. We had a whole, and now we only have 0.65. Just like up here, we had 15,000, and now we wanted 35,000. We have one whole rock, now 65%. So we need to solve, and notice that what I'm solving for is in the exponent. I'm not going to take the natural log of each side because I don't have an e. I can take the log of each side. So the log of 0.65 equals, I don't need to have that 1 there, the log, because 1 just keeps it the same, of 0.5 to the t over 1,500,000,000. I'm going to move my exponent to the front. So I have log 0.65 equals t over 1,500,000,000 log of 0.5. Well, normally at this point, we don't have something here. Like up here in this problem, we were just left with x. But here we've got this other number we still need to do something with. So if I multiply both sides by 1,500,000,000, these will cancel, and now it's over here. So I have 1,500,000,000 log of 0.65 equals t times the log of 0.5. Well, I'm solving for t, so I'm going to divide both sides by log of 0.5. And now I just have to put this in my calculator. I'm going to do my division of logs first. Log of 0.65 divided by log of 0.5. And then I'm going to multiply that by 1,500,000,000. So 1, 2, 3, 4, 5, 6. And I get 932,232,565.1 years. It's pretty old. It's an old rock. All right, let's go to example 4. The 1989 population of Mexico was estimated at 87 million. Its annual growth rate is 2.4%, so that's 0.024. Estimate when the population will reach 100 million. Okay, so this is not PERT, because it doesn't say it's growing continuously. It's just growing at a constant rate. So this is where we have the principal times 1 plus r to the t equals the amount. So I know that I have 87 million. 1 plus 0.024. I don't know the t. And I know that I want 100 million. Okay. All right, so I'm going to need to divide both sides by, oh, I can't, because it's being multiplied there. So I'm going to need to take the log of both sides. I'm going to have to do that right now. Okay, so log of both sides, I'm going to take the log of this and the log of this, and I get the log of 100 million equals the log of 87 million times 1.024 to the t. I could have actually, I did not want to do my log there. So sorry. I think it was this 1 plus that was just throwing my brain off for a second. I need, sorry, just sometimes I gotta think through the problem for a second. Because I want this 1.024 to the t to be by itself, I can divide both sides by 87, because this is multiplication here. This is not being raised to the exponent. This is being multiplied, so I can divide. Okay. Sorry. My brain had a little hiccup there for a second. Because, again, I just want to emphasize this 87 million is not being raised to the exponent, so I can divide. And let's see what I get when I take 100, 1, 2, 3, 4, 5, 6, divided by 87, 1, 2, 3, 4, 5, 6, 6 zeros in million. All right, I get 1.024 to the t equals 1.149425287. I don't think this is going to convert. Oh, it did. 100 over 87. Duh. Of course it did. 100 over 87 equals 100 over 87. All right. Now I can take the log of each side. So the log of 1.024 to the t equals the log of 100 over 87. Take the log of each side, which means we can move the t to the front. So the log of 100 over 87 equals t times the log of 1.024. The only thing I have left to do is, this was a page number, sorry, this 19 was something. I'll get rid of that. There you go. You're going to divide both sides by the log of 1.024. These cancel. And let's see what our time is. Let's put this into our calculator. I've got the log of 100. Log of 100 divided by 87 divided by the log of 1.024. 0.024. And there's my answer, 5.